So today's topic will be differentiability and analyticity of a complex valued function, right? As we were discussing in our last video, the limit and continuity behavior of a complex valued function. So this video will be continuing that topic with the differentiability, right? And as we know that from real analysis, when we say that a function fx is differentiable, when the left hand derivative is equal to the right hand derivative, right? But here, since we are dealing with a complex number and there is not a concept like left hand and right hand, because we are dealing with a complex plane, a point on complex plane. So suppose we have some point z equal to z naught on complex plane, then the differentiability criteria is given by this definition: a function fz, this is a complex valued function, z is a complex variable, as z equal to x plus iota y. A function fz is said to be differentiable at the point z equal to z naught in complex plane if f dash z naught equal to limit z tends to limit delta z tends to 0 f z naught plus delta z minus f of z naught over delta z exist uniquely, or we can say exist, right? So we say that a complex valued function is differentiable at some point z equal to z naught is a point on complex plane, and if this limit exists, right, then we say that the function is differentiable at that point, right? And the derivative of the function is given by this formula f dash at z naught. If this exists, then the derivative will be given by this value of this limit, right? And you can see that here we have delta z. Delta z is a small change. Suppose you have a point z equal to z naught on a complex plane. You can think a complex plane like a big ground, right? And z naught is some point on that ground, right? Complex plane. And you say that the function is differentiable at that point if within the small neighborhood of z naught, or you can say that for a small change in z naught, you can say delta z is a small change, right? And the value of the function in the neighborhood of, in the small neighborhood of that point is z naught, and this indeed represents a small neighborhood. Z naught plus delta z means z naught is your point of interest and delta z is a small change, right? In any direction you can approach a point on complex plane from infinite number of directions, right? So delta z is a change in any direction, right? So the value of the function taken at that point, neighborhood point, minus the value of the function at the point we are interested in, z naught, divided by the change delta z. If it exists uniquely, then we say that the function is differentiable and the derivative is given by this f dash z naught, right? So this is the formula to find the derivative of a function at point z equal to z naught, and I will exhibit a small example for this. Suppose I take, for example, take the function if fz equal to z square plus 1, right? And we have to check its differentiability, right? For example, this is differentiable at all points on complex plane, right? This function is differentiable at any point on complex plane, right? And we'll use this formula. Take z naught, z equal to z naught, an arbitrary point, right, on complex plane, right? Okay. Then using this formula, then f dash z naught is equal to limit delta z tends to 0, f of z naught plus delta z, that will be I think z naught plus delta z is square plus 1, right? This is the value of f of z naught plus delta z, right? The value of the function in the neighborhood of this point, right? A small neighborhood, minus f of z naught, and that will be z naught square plus 1 and divided by delta z, right? And on squaring it, I will get delta z square will be cancelled, 1 and 1 will be cancelled. I will be having delta z will be common, and delta z plus 2 times of z over delta z. Then you can cancel this delta z. We'll be having limit delta z tends to 0, delta z plus 2z, and on approaching delta z to 0, this will give me 2z, or should I write it as z naught? Z naught, right? So you can see that the value of the derivative at point z equal to z naught is equal to twice of z naught, and z naught is any point, any arbitrary point. You can take z naught equal to 1, 2, iota, 1 plus iota, 2 plus 3 iota, any point on complex plane. So this shows that this the value of this limit exists uniquely. You can see that first thing is that there is a delta z in the numerator and denominator that was cancelled out in the calculation, and that indicates that the function is differentiable at all points. Means when you have this delta, means the term in the denominator gets cancelled, then the function comes out to be differentiable. Roughly you can say that, right? Okay, so this is an example supporting this differentiability of a function, and then I will give you another maybe a non-example which is not differentiable at all points, right? And yeah, let me take it example 1. Show that fz equal to x plus 2 iota y is not differentiable at any point on complex plane, right? So this is the kind of non-example, and solution. Here we can see that our fz is not expressed in terms of z. In previous example, fz was explicitly in terms of z, but in this case it is in terms of x and y, and you cannot write it in terms of z, right? And let me apply this formula. First I should write this f of z naught plus delta z. Let z equal to z naught be arbitrary point, right? Then first I will write f of z naught. For this one I will be getting x naught plus twice iota y naught, right? And then I will write f of z naught plus delta z, and that will be given by here f of z naught plus delta z means actually z naught is nothing but x naught plus iota y naught, because z is x plus iota y, and delta z will be delta x plus iota delta y, right? Then it will become f of z naught plus delta z will become x naught plus delta x plus twice of iota y naught plus delta y, right? And you have to remember that this delta z is equal to delta x plus iota delta y, right? You want a small change in z, right? And that indicates a small change in x as well as a small change in y, because z is equal to x plus iota y. Z is a complex variable, right? X plus iota y. Okay. Then plugging these values here in my formula, then f dash z naught equal to limit delta z tends to 0, f of z naught plus delta z is this one, x naught plus delta x plus twice of iota y naught plus delta y. then minus f of z naught, you can see from here, right, x naught plus twice of eta y naught divided by delta z, and indeed that delta z is equal to delta x plus eta delta y, right. Now we can see that on opening these brackets, this x naught and x naught will be cancelled out, and twice eta y naught will be cancelled out, and we will be left with delta x plus twice of eta delta y, right, equal to limit delta z tends to 0, delta x plus twice eta delta y divided by delta x plus eta delta y, and remember that this delta z is actually equal to delta x plus eta delta y, right. Okay. Now you can see that in contrast to the last example, supporting example, luckily this delta z was cancelled out in calculation, but this is not the case with this example, right. You cannot cancel these, right. So you have to consider the different path along which this delta z tends to 0, because we have something in the denominator, right. You cannot substitute directly delta x equal to 0 or delta y equal to 0. In case you substitute delta x equal to 0 and delta y equal to 0, because this is ultimately delta x plus eta delta y, then you will get 0 by 0 form, right. And obviously you don't need 0 by 0 form, you need some value, right. So I will evaluate this limit taking two cases, as we have been taking in our last videos regarding continuity and limits of complex valued function. Once I will take delta y equal to 0 and another time delta x equal to 0, means approaching this point z naught from two directions, right. Because z naught is an arbitrary point, you can see that, and since it is an arbitrary point, I should represent it here this way. This is my y-axis, this is x-axis, and this is obviously z-plane, right. We are talking about z-plane, and this is my point z equal to z naught. Suppose I take this point here, right, in first quadrant. This is my point z equal to z naught, right. Now you can approach this point from two directions, right, either from, not from two directions, from infinite number of directions, but here we will have only two directions, once along parallel to x-axis and then parallel to y-axis, then we will be done, right. If I approach this point z naught parallel to x-axis, either from right or either from left, right, this is a direction approaching z naught parallel to x-axis, you can see that. And if you approach this point z naught parallel to x-axis, in that case this height will not change, right, and that indicates that height means delta y will not, delta y is equal to 0, y will not change, means delta y will be 0. Delta y indicates the change in y, right. When you approach z naught from this side, you can see that the x is continuously changing, right, but not y, and since y is not changing, then delta y will be equal to 0, right. So for this, delta y equal to 0, right. Okay. As delta z tends to 0 along a line parallel to x-axis, that is delta y equal to 0, right. Geometrically it means that we are approaching the point z naught along a line parallel to x-axis, right, and analytically we can say that delta y equal to 0, right. Then substituting delta y equal to 0 here, I will be getting, gives f dash z naught equal to, now plugging this delta y equal to 0 will give limit delta z tends to 0, but now I only have delta x, because delta y will be 0, then everything will be in terms of x, so you should write delta x tends to 0 rather, right. Delta x over delta x, and that will be cancelled, and we will have 1, right. And now approaching this z naught from another direction, now parallel to y-axis, suppose this direction, right, or from this direction. You can see that when you approach this point z naught from this vertical direction, you can see that y is continuously changing. Either you approach from upward or from this downward, right? Then y is changing but not x, right? X is same. So we write delta x equal to 0, right? As delta z tends to 0 along a line parallel to y-axis, that is delta x equal to 0 gives f dash z naught equal to limit delta y tends to 0, because everything will be converted in y, right? Delta x equal to 0 will produce 2 iota delta y over iota delta y, and that will produce 2, right? And now we can see that when we approach this point z naught along horizontal direction, we are getting the value 1 of this limiting value of this function, and when we approach this z naught from along a line parallel to y-axis, we are getting a different value. And since these values are different, means that limit is not unique, and that contradicts this thing. Exist means exist uniquely, right? You are getting the same value every time, regardless of the curve you are choosing to approach this point z naught, right? But this time I have taken only 2 curves and I am getting different value. So I can say that this limit doesn't exist, right? And hence the function is not differentiable at this point. What point? Z naught, means at any point, right? Since limit is not unique, or we can say limit doesn't exist, therefore fz, this function, first was this function x plus iota y, x plus 2 iota y, is not differentiable at any point z equal to z naught, right? So this is a non-example which is not differentiable at any point on the complex plane, right? And this is a supporting example which is differentiable at any point on the complex plane, right? And we have some examples which are differentiable at one point, right? Okay, let me take it to another level, that is called analyticity, right? Differentiability and then analyticity. And obviously this analytic behavior of a function depends on the differentiability of a function, means these two topics are related. Once you understand the differentiability of a function at a point, then you will be able to understand the analytic behavior of a function at that point, right? So we will be taking this differentiability to another level, and that is called the analyticity, right? Okay. Okay, so analyticity of a complex valued function, a function fz is said to be analytic at point z equal to z naught if it is differentiable at z equal to z naught and at all points in the neighborhood of z equal to z naught, right? First I will tell you the meaning of this term neighborhood, right? What is this neighborhood, right? You can recall from the real analysis of function of real variable, when you say that suppose this point is x equal to 1, this is x-axis, right? In real calculus, this is x-axis. When you say that the neighborhood of this point x equal to 1, this is x equal to 1, right? Neighborhood means a small interval, right? A small interval like this, right? Taking all the values in the neighborhood of 1, right? Means the neighborhood in one variable function. When you talk about fx, one variable function, the neighborhood is called the left hand side and right hand side values of that x equal to 1, right? Means all the neighboring values which fall on the left as well as right hand side of that value we are talking about, right? Or you can write it as this way. It indicates that a small interval of this nature, x 1 minus epsilon comma 1 plus epsilon, and this interval is open. Open interval means the endpoints are not included in the interval, right? 1 minus epsilon is a very small number. Epsilon is a small quantity, right? This is called the neighborhood in case of real function, right? Means the close values which fall on left and the close values which fall on right of that number we are talking about, right? Okay, but in case of complex valued function, we are in z plane. We are not in on x axis. We are on z plane, right? So when we talk about the neighborhood of some complex number, then it does mean that this is z equal to z naught, right? Z naught, okay, and this is a complex plane, x axis and y axis, right? And you call it z plane. Then your neighborhood means this, not an interval, but more general, and that it should be a disk, an open disk, because this was an open interval, then open disk, right? Disk means all points inside this open circle will constitute a disk. You can see that, right? There are infinitely number of points inside this disk, open disk without a boundary, right? And you write this in this way: mod of z minus z naught less than epsilon, right? Actually, it indicates a circle. Mod of z minus a equal to small r is a circle on complex plane, right? Okay, so indicates that all values of z which are close enough to this point z naught within an epsilon distance of it, right? Means, as I said in case of real function fx, this was for fx. For fx, we have this thing, neighborhood, and for fz, we have this thing. So these are two different pictures. The upper picture is for real function, while the picture below is for complex function. And you can see that the interval here is actually a one-dimensional interval, you can say that, right? Along x-axis only. It means the close values which are on left of 1 and the close values which are on the right hand side of 1. But in this case, for fz, the neighborhood is of z naught is those points which are very close to this z naught, right, and which are within the epsilon distance from this z naught, right? Or you can say this is an open disk, right? So whenever we talk about the neighborhood of a complex number, we think about a small disk, right? Small disk of epsilon radius, right? And there will be infinitely number of points inside that disk, right? Okay. Right, I will come to the definition. When we say that a function is analytic at some point z equal to z naught, you can see this picture. You can see this point z equal to z naught. That is obviously the middle point of this disk, and this disk is very, very, very small, infinitesimally small, as you can think, right? Okay, so this is a point z equal to z naught, and you are talking about the analyticity of the function at this point, right? But when you talk about the analytic behavior of a function, at some point you have to consider all the points falling in the neighborhood of that point, right? Means analyticity is not a point property, rather it is a neighborhood property, right? We are interested in find the analytic behavior of a function at the point z equal to z naught, but at the same time we should take interest to the points which falls in the neighborhood of it, right? So if you read the definition, you can understand that a function is said to be analytic at the point z equal to z naught if it is differentiable at that particular point we are talking about, z equal to z naught, as well as, right, all the points falling in the neighborhood of that point, right? Means it is a strict criteria of differentiability, right? Differentiability at a point is related to the point only, but analyticity at a point is related to all the points in falling in the neighborhood of that point we are concerned with, right? Okay, So this is the definition for analytic function, right? Means a higher order of differentiability, you can say that, right? Okay, and I will take an example of this analytic function. For example, I have rubbed that example. Fz equal to z square, right, is analytic everywhere, right? Fz equal to z square is everywhere analytic, right? If you check the differentiability at any arbitrary point, as I have checked the differentiability of fz equal to z square plus 1 at an arbitrary point z equal to z naught, then on evaluating this limit, this one, I will be getting answer as twice of z naught, right? Okay, you can verify it by yourself. The answer will be twice of z or twice of z naught if you take an arbitrary point z equal to z naught. It means that this function is differentiable at any point, right? As we have got in this example, I have rubbed that example. This function is differentiable at any point. And what does it mean? If this function is differentiable at any point, means this function will be analytic, obviously, right? Because any point means z equal to z naught, and all the points which will be in its neighborhood of z equal to z naught will give the analytic behavior, right? Any point means which is differentiable at any point will automatically produce the function, an analytic function, right? Okay, let me take a non-example for this, which is non-analytic, or should I take fz equal to z bar, right? Verify yourself. Okay. Example number 1. Fz equal to z bar is nowhere analytic, right? Nowhere analytic means not analytic any of the point on complex plane, right? And again, I have to rely on the definition of differentiability, because analyticity is something that is related to differentiability, right? And I have to choose an arbitrary point. Let that point be z equal to z naught. Let z equal to z naught be an arbitrary point on complex plane, right? Now I am going to check its differentiability at z equal to z naught. Then f dash at that point z naught, right? Note that we are checking the analyticity of a function f z, but we start with the differentiability at that point we are talking about, right? Okay, f dash z naught limit delta z tends to 0, f of z plus z naught plus delta z minus f of z naught over delta z, and on plugging this value here, and one more thing, this z bar is actually equal to x minus eta y. Z bar indicates the conjugate of z, right? And that is x minus eta y, right? And for that, since fz equal to z bar equal to x minus eta y, you know that, then f of z naught plus delta z will be something like, because z naught is actually x naught plus eta y naught, and that will produce x naught plus delta x minus y naught plus delta y, right? And f of z naught is equal to x naught minus eta y naught, and let me plug these values here. Then I should plug it here. This is my reason. Okay. Equal to, right? Plugging these values here. This minus this, then ultimately x naught will be cancelled, minus eta will be here, I think eta. Okay, I will be getting something like limit delta z tends to 0, and yeah, delta x minus eta delta y divided by delta z, and that is actually delta x plus eta delta y, right? Fine. And for this step, I'll put a star here, limit, or this is the reasoning since this one. Okay, fine. Now again you see that this delta z is nothing but delta x plus iota delta y tends to 0, and if you plug delta x 0 and delta y 0, we'll get 0 by 0 form. Means it indicates that we have to consider different paths as I considered here in this example, right? Along a line parallel to y axis and then parallel to x axis. Okay, so similar to that proceeding as this one. Okay, first I will choose delta y tends to 0, and that will produce delta x over delta x, right? And that will give 1, right? Similar to this one. Right, that will produce 1, and if I choose delta x equal to 0, then I will be getting minus 1, right? So two different values of this limit for two different paths, mean the limit is not unique, right? So I will write it here, choosing delta z to 0 along delta y equal to 0 and delta x equal to 0. Along, this means along a line parallel to x axis, and this means along a line parallel to y axis. I am not writing that incomplete. Will produce give limit delta z tends to 0. First it will give 1, and second time it will give minus 1, and you can see that these two values are different, right? And since these values are different, this limit doesn't exist, means the function is not differentiable at this arbitrary point, or you can say that the function is not differentiable at any point, right? Therefore fz equal to z bar is not differentiable at point z equal to z naught, or you can say that it is not differentiable anywhere, nowhere differentiable and then nowhere analytic, right? Okay, so taking another example, example number 2, fz equal to mod z square is not analytic at any point, or you can say that it is nowhere analytic, right? But differentiable at origin, right? Or you can say that and not analytic at origin but differentiable at origin, right? And in this example you will see the difference between the analyticity and differentiability, right? Okay, solution. Obviously I have to start with the differentiability, right? Because analyticity is something strict criteria than differentiability. So checking differentiability first. Should I take z equal to z naught or z equal to 0 for origin at any point? Okay, right. Okay, I should is not analytic at z equal to 0 but differentiable there. Okay, but differentiable there. Okay, I'm checking out it for z equal to 0, right? Right. Limit delta z tends to 0, f of z plus delta z minus f z over delta z. This will have dash z, right, from definition. Okay, fine. And if I choose an arbitrary point, then let me write it in terms of x and y first, right? Here fz equal to mod of z square and mod x plus iota y square, and you know that modulus of a complex number x plus iota y is equal to square root of x square plus y square, and that will produce x square plus y square, modulus of a complex number, right? The square root gets cancelled with this square, right? And let me write then f of z plus delta z will produce x plus delta x square y plus delta y square, right? And okay, fz is this one, fine. Therefore, f dash z equal to limit delta z tends to 0, x, subtracting this from this, plugging those values here, I will be getting delta x square, okay, x square to twice of delta x, that will produce delta x plus twice of x plus delta y plus twice of y, yeah, twice of y over z, delta x plus iota delta y, right? Fine. And since we need to check the differentiability and analyticity at z equal to 0, so plugging x and y equal to 0, right? I have missed y here, I think. No, fine. Okay. At z equal to 0, that is x equal to 0 and y equal to 0, I will get, we have f dash 0, right? We are checking the differentiability and analyticity at z equal to 0. Limit, this will become delta x square plus delta y square. The denominator I will be having delta x plus iota delta y, and then delta z tends to 0, right? You can see that this will go to 0, this will go to 0, right? And using the formula for a square plus b square, there is a plus b multiplied by a minus a plus iota b multiplied by a minus iota b, right? Limit delta x minus iota delta y, right? Applying the formula of a square plus b square, there is a plus iota b multiplied by a minus iota b. So a plus iota b will be cancelled out, and delta x plus iota delta y will be cancelled out, and you will be left with this, right? Okay, fine. So what will be that if delta z tend to 0? Okay, fine. Should I choose it an arbitrary point z naught? In that case, this will go to 0. Fine, no, 0. Delta x go to 0, this will be 0, and we will left with this. Okay, delta y will be cancelled. Fine, I should take it arbitrary point, right? But differentiable there. Okay, fine, leave it. Z, taking z equal to z naught, right? That is x equal to x naught and y equal to y naught, right? And in that case, it will be f dash z naught, right? And then it will become, I am trying to produce a more general result, right? And that will produce here, okay, delta x plus twice x naught plus delta y plus twice of y naught divided by delta x plus iota delta y, right? Okay, now I have to choose two different paths as I did earlier. Choose delta z tending to 0 along a line parallel to x-axis, and that is actually delta y equal to 0, and that will give me f dash z naught. Okay, delta y equal to 0, this will be 0, delta x will be cancelled out, and delta x tending to 0, this will be 2x naught. Limit delta x tending to 0, delta x plus twice of x naught, right? You can see that this will go to 0 and eta delta y will go to 0 and delta x will be cancelled out. You are left with this one, and putting delta x 0, you will be getting twice of x naught, right? Fine. I'm taking a more general case, right? Because I have to show that this function is not analytic at z equal to 0 as well as not any other point, but differentiable at 0, right? So this is what we got on choosing delta z to 0 along delta y equal to 0. Now choose delta z to 0 along delta x equal to 0, means a line parallel to y axis, right? And that will gives f dash z naught limit delta y tends to 0. Putting delta x equal to 0 here will produce these two terms only. Delta y will be cancelled, and I will be having delta y plus twice of y naught over eta, right? And on plugging delta y equal to 0 here, I will be getting twice of y naught upon eta, right? Equal to twice of y naught over eta, or you can rationalize it with plus eta, right? You will be getting minus eta twice y naught, right? And along two different paths, values are different. You can see that this is twice of x naught, this is minus times of twice of y naught, and obviously this is a real number because x naught, you can see from here, z equal to z naught means x naught plus eta y naught. X naught is real, y naught is also real, right? Okay, so this is a real number and this is a complex number, right? And a real number cannot be equal to a complex number, right? We are eta here, right? Having eta here, and in case you want them equal, obviously in that case it has to be 0, because putting x naught equal to 0 and y naught equal to 0 will produce 0 equal to 0. That will be the only possibility, right? Or you can proceed it here as what do we want for differentiability? What do we want for differentiability? We just want these two values to be equal, right? We want twice of x naught equal to minus eta twice of y naught. We want this. If we want that this limit exists uniquely, we want these two values to be equal, right? And then taking it here, you will write x naught plus eta y naught equal to 0. 2 will be cancelled out, and that is actually z naught equal to 0. It means that if we want that these two limiting values are same, right, then that will happen only at this point, and that point is the 0 point. Means the function is differentiable. Obviously we can call it differentiable because the limiting value is same in both paths. The function is differentiable only at this point, z naught equal to 0, and not at any point, right? And what does it mean? If the function is differentiable at only point z naught equal to 0 and not at any other point, it means that it cannot be analytic, because analyticity is the open set property. The function has to be differentiable at that point we are talking about, and in the neighboring points also, right? But in this example, the function is differentiable only and only at the single point, and that point is z equal to 0, right? And not anywhere else, right? So it indicates that the function is differentiable at z equal to 0, but not analytic at z equal to 0, right? Therefore, fz is differentiable at z equal to 0, but not analytic, right? And you should understand the reason why I have written not analytic, right? Differentiability is okay, that's obvious from these steps. They will be equal if this is equal to 0, right? But this is the only point at which the function is differentiable, and you need some more points in the neighborhood points where the function is also differentiable, and in this case it is not the case, right? So the function is differentiable at z equal to 0 but not analytic at those points. So we have taken 2 or 3 different kind of examples. An example which is nowhere analytic, right? An example which is analytic at one point, right? Okay, and a previous example fz equal to z square, this one, which is everywhere analytic, right? You can check this definition for this point and you will get a good looking derivative, right, along any path. So this is the differentiability and analyticity of a complex function, and let me tell the what does it mean geometrically. What can you say that what is the meaning of f dash z? Because you know that f dash x, the derivative of a real function, indicates the slope of the tangent at that point, right? Means if you write f dash of a is any point, then it indicates that the slope of the tangent to the curve at x equal to a, right? In case of real function. But in case of complex function, because we know that it is very hard to visualize the graph of a complex valued function, so it is also difficult to say that what does it indicate f dash z in general, right? However, in case of if we consider it as a linear mapping, as we have discussed in our previous lectures, fz is equal to az plus b, linear mapping, complex mapping, where we considered z plane and w plane, right? The domain and the codomain. In that case, that f dash z will indicate the magnification, right, at any point, right? Or more generally, you can say that the magnification and the rotation, if the magnification and the rotation is uniform throughout the domain, right, of a complex valued function, then we can say that the function is analytic, right? Because in case of a real valued function, when we say that fx is differentiable at some point, we automatically interpret that the function is, the graph of the function is smooth, right? The parabola graph is a smooth graph. It is differentiable everywhere, right? But this graph is not differentiable. If I draw this graph, a graph having a sharp corner here, this graph is for mod x, you know that, right? The x-axis and y-axis. At this point, it is not differentiable. Not differentiable, right? Not differentiable at this point, where you have this sharp edge or sharp corner, right? In case of real function. But in case of complex function, that is something different, right? But you can say that, or again, you can see that this is the graph of mod x, right? Okay, and if you draw the graph of mod x square, if you square it, all right, it will become smooth at this point. The graph of mod x square is like this one, right? Parabola, fine. And in that case, it will be differentiable at this point. You can see that the curve is smooth at this point, right? And that indicates the differentiability in real function, right? Smoothness indicates the differentiability in case of real function, and this is differentiable at this point 0. But you can see that this example, fz is equal to mod z square. In place of x, I have taken z. This is not analytic at any point, right? And see the contrast nature of the complex valued function with respect to the real function. Mod x square is everywhere differentiable, right? You can see that the graph is smooth everywhere, right? But mod z square is differentiable only at origin and nowhere analytic, right? So these are some interesting facts about if you compare a real function with the analog complex function, right? And and one more thing, if you check the analyticity of a complex valued function at some point, you can see that you not only check the differentiability at z equal to z naught, but you need to check the differentiability at all the points which are in the neighborhood of this. And obviously there are infinitely number of points in the neighborhood of z equal to z naught, and practically that is very difficult to check the differentiability at all of these points. So we need some concrete theorem or concrete formula to check the analyticity, right? Because checking differentiability is different thing, but checking analyticity needs some bigger aspect, which needs some more points or points in the neighborhood also, right? And practically that is impossible. So we'll be needing something different, means to check the analyticity of a complex valued function, and that will be the part of our next video that are called Cauchy-Riemann equations, right? Simple test to check the analyticity of a function at some point. Rather checking the differentiability at all the neighborhood points, will just have one formula which will prove the analytic or non-analytic behavior of a complex valued function. That will be part of our next video. For this video, thanks.